Good morning, everyone. Am I audible? So can we start, or we should wait for another 1 minute to join by other candidates? Please. Lecture 2 घंटे बाद. Yes, so for your information, let me tell you, we have uploaded all the slides on this Canvas platform, and the link for this course, you have the YouTube link that is also being shared on the Canvas platform. So please visit. If you have missed some of the lecture, you can go through that, and it will actually bring you at par. Okay, so let us start for the day. Where you can see in the canvas, I'm sharing you the link. Dr. Geeta, you may start. Stop recording. It's already been started. I'm not able to write in the chat box. Dr. Geeta, can you hear me? I'm not able to type anything in the chat box. Yeah, now it is there. So I have shared you the link where the canvas, you will go to the course, then files, then go to the folder, and you will be having the course material over there. I hope it is going to work for all of you. Okay. So now let us start it. So yesterday we have missed one lecture. That's what I'm going to take it today, because the next couple of lectures will be taken by Dr. Deepak Bharati, and he will be having the topics which are related to MOSFET. So before that, we have to cover MOSFET. So first today I'm going to cover MOSFET, and after that, if time permits, we'll take some numericals based on clippers and clampers. And maybe half wave rectifier and full wave rectifier we will be having. Some of the numerical portion will be having. Okay, so I hope my screen is visible to all of you. If it is not, please let me know. You may type in the chat box. I am able to see the chat box. If there is some issue, any question is there, please feel free to type in the chat box. Okay, so let us start for the day. This PPT probably I have not shared. I will share. If it is not shared, I will share after the end of the class. I am going to share it soon. Fine. So let us start for the day. MOSFET, as the name suggests, it is metal oxide semiconductor field effect transistor. Metal oxide semiconductor field effect transistor is the name MOSFET. Now, why we are going to use it? So MOSFET is a FET, field effect transistor, means because of the electric field, the transistor is going to work. And there is a metal, first of all, there is a metallic structure, then there is oxide structure, and after that a semiconductor structure is there. So that's what we call this is MOS structure or MOSFET structure. So this type of structure you will be having. On the top of this, it is metal. After that, this color is white color is your oxide, and below that there is the channel, that is nothing but the semiconductor structure. This third layer is the semiconductor structure. So this becomes MOS structure. The bottommost, this is the substrate which might be made up of silicon or might be made up of silicon dioxide or some any other material. Okay, so you can see in the next diagram, it is metal, then metal oxide, insulator, and then the semiconductor you will be having. So that's what it is, MOS structure. These are of two types, NMOS and PMOS type. These are the symbols given for each of this. This is the N-channel MOSFET. Here, NMOS means it is N-channel. We are talking about channel. There are two types of transistors, NPN and PNP. NPN transistor says that one is N-type semiconductor, then P-type semiconductor, then again N-type semiconductor. So you can say NPN transistor is made up of two back-to-back connected diodes, right? Although it is not going to happen, but you can think of that there are two diodes which are connected back to back and you are getting one transistor. But in case of MOSFET, it is, you can side it is N, this side is also N, and this is P type, right? The channel is P type. But this P type channel is getting converted to N type when this is going to work. Means whenever the device is on, then ample number of electrons will be coming to this this channel. Those will be electrons. Electrons means negatively charged movable particles. Okay, so because of that reason, we will be calling this N MOSFET. Please remember. Likewise, a P channel MOSFET or P MOSFET is the one in which both of these source and drain will be made up of p-type, and the channel is made up of n-type. And whenever the device is on, we have ample number of holes running through the channel, and that's what we'll be calling that. This is the PMOS device. Okay, these are the symbols. So you have a gate, and you have a drain, and you have a source. In BJT, what are the three terminals? Can you type in the chat box the three terminals for the BJT? Yes, please type in the chat box the three terminals of BJT, NPN transistor. What are the three terminals for BJT? Very good. Emitter, base, and collector, right? So emitter, the name suggests emitting the electrons or the carriers. Collector is collecting all those, and base is there to modulate, right? Likewise, in this also, gate is the control. Okay. And source is the source of carriers. Let's say this is n-type, so it means it is the source of n-type carriers. Those are electrons, and these n-type carriers are going towards source to drain. Where this will be going, this is having the ample number of electrons. These are the red dotted are the electrons. These electrons are going through this channel into the drain. So it means from source, we are taking these to drain via the gate control. Okay. You can think of that the source is like a water tank. So in a water tank, water particles are there, and these are equivalent to electrons. Now we are going to open the tap. So opening this tap is the gate control, how much you can open it. This is your gate. So if you are opening this more, it means more water is going to flow. And then this will be coming into this bucket that is nothing but drain. Okay. And this flow of water, that is rate of flow of water, that is dq by dt, equivalent to dq by dt. So we'll be calling this as current flow. So more the control you are going to open, it means more the flow from there to here is. It means more water is going to flow, and this is contributing more amount of current. This is actually the analogy of your NMOS operation, NMOS or PMOSFET operation, right? So the gate control is there from source to drain. There are carriers controlled with the help of gate, and then these are moving towards the drain. Okay. These are the symbols. These are two symbols, standard symbols to be used. In some other books, this is also termed as 4-terminal device. In a 4-terminal device, you will be having it in this way. And then the third terminal is the base terminal. Body terminals, substrate or the body terminal. And likewise, it will go in this way, and this is going to come. N stands for not pointing, just like in your BJT. This arrow outside shows this is not pointing. NMOS. This is NMOS, right? So in NMOS, it is not pointing inside the device. In PMOS, it is pointing inside the device. Remember, in PMOS, source is at the higher potential, while in NMOS, source is at the lower potential. So these are the three terminals: gate, source, and drain. So the current in PMOS will flow from source to drain. Current flows from the higher potential to the lower potential. But in case of NMOS, the current is going to flow from VD to VS, because higher potential is VD to VS. Another thing is, in BJT, we have NPN doping, but this collector doping, collector width, and the emitter doping, emitter width, these are different. And if these are different, we cannot interchange both of these. But in case of MOSFET, this is your drain and this is your source. These can be interchanged because the doping of both of these is equal. Both of these are having the equal doping, and because of that, you can interchange both of the source drain, and still it will be working fine. So you are not physically interchanging that. What you are going to do is, if you are going to apply, let's say 1 volt over here and 0 volt over here, automatically this becomes a drain, and the second one, which is having the lower potential, becomes source. But likewise, if you are making it, let's say zero point 0.5 potential, zero point 0.5 volt, and the other one, let's say you are making 1 volt. So which one is the source in this case, left or right? Which one is the source in this case? I have taken one scenario, 1 volt and 0.5 volt. So tell me which one is the source and which one is the drain in this case. So left one is source or drain? Just type in the chat box. So higher potential, we are seeing it is n-channel device. So higher potential is going to be drain. You can look over here. This is 1 volt. Left side is 1 volt. So this 1 volt is going to be drain, right? So this is going to be drain. And this is 0.5. 0.5 is lower than 1. So it is going to be source. We are only looking at the higher potential and the lower potential. So the current is going to flow from this to this, right? Higher potential to lower potential side. And the electrons will flow from lower potential side to higher potential side, because the electric field is developed in that direction, that it is going to push the electrons from the lower potential towards the higher potential side, right? And that's the reason the source and drain are physically, there is no need to interchange, just electrically you can interchange by modulating the external applied voltage, right? And then this is work fine. So basically MOSFET is a 4-terminal device, but most of the times we'll be using 3 terminals. The 4th terminal, we will be presuming that this is tied to the source of it. By default, we'll presume that this is tied to the source of it. If it is not explicitly mentioned, we'll presume that the 4th terminal is automatically tied to the source of it. And if we are using these type of 4-terminal symbol and arrow type of symbol, in that case, there is no need of this bubble in PMOS. So in the simplest form, the MOSFET is having this symbol. This is one symbol. And PMOS will be having this symbol. A bubble says that it is PMOS. Another symbol, you can have arrow over here and arrow over here. And this will not be there. This bubble is not be there. That is the other symbol, right? And the 4th symbol is, you will be having this 4th symbol. In this, your body is connected to the source. The substrate is connected to the source and the bubble is not there. So these are the different symbols used in the literature for the MOSFET. So basically MOSFETs are of 2 types, enhancement type and depletion type. Enhancement type is normally off, which we will be using most of the time, that is enhancement type, normally off. If we talk about NMOS, so the VTH is more than 0 for NMOSFET. And for PMOSFET, we usually have VTH less than 0. So at 0 potential, 0 gate voltage, enhancement type is normally off. Depletion type is normally on device. So depletion type, in order to represent whether it is enhancement type or depletion type, we'll be doing like this is the normally off device, that is represented like NMOS enhancement type. If you want to make a depletion type, just darken this edge so that it is going to tell that okay, the width is more and it is depletion type. So that's normally on device. In order to make off depletion type, what you have to do, you have to apply the negative voltage, so that, because for NMOS, you can see over here, it is normally on. VGS is equal to 0, it is on, because VT is less than 0 even for NMOSFET. That's what it is normally on. So in order to make the device off, what you have to do? You have to decrease the VGS below the VTH. Let's say my VTH is minus 0.5 volt for NMOSFET depletion type. So it means I have to decrease my VGS lesser than this value. Maybe minus 0.6, minus 0.7, something like that. If I will be doing my VGS, then only it is going to work. Otherwise, it is going to make the device off. Otherwise, the device is already on. On the basis of what type of carrier is contributing to the current flow, it is divided into two parts, N channel and P channel. N channel is termed as N MOSFET, P channel is termed as P MOSFET. So these are on the basis of carrier type, that what type of carrier is there. So these are the symbols used for the depletion type and enhancement type, N MOSFET and P MOSFET. So the upper one in the upper one, both of these are actually having the P plus region and P plus region and N type substrate. So this is the example of P channel MOSFET. And the below is also the example of P channel MOSFET. In the first example, there are no biasing conditions, nothing is being applied. In the second one, VGS voltage is being applied at the gate terminal and VDS voltage is applied at the drain terminal. So you can have a look. If it is P MOSFET, you can see the reverse of the VDS, means the negative is attached to the drain of the device, and that's what it becomes actually the lower potential as compared to your source in case of PMOS. In PMOS, source is at the higher potential. So if source is grounded, it means lesser than the ground potential you have to apply at the drain. That's what the negative potential is being applied. So it is equivalent to that you can apply VDS positive at the source and you can ground the drain. So that will be equivalent. And the flow of current will be happening from this to this way. Why? Because source is having ample number of holes. These holes are going towards the drain. So we know that holes are positively charged particles. So the formula P, Q, mu, E. Mu P into E. That was the current density we have discussed already, right? Or let's say sigma E. So here PQ, that is the positively charged particles. So that's what the flow of charges are having the direction of the current flow also in this particular case. So the current is flowing in the same direction as the flow of current, the charges are there. While in case of NMOS, the current is flowing in the opposite direction because you will be having minus NQ charge. Total charge is minus NQ. So the flow of charge is in one direction, electrons are in one direction, and the current is flowing in the opposite direction. And these are the typical symbols which are used in the literature for the depletion type. This is enhancement type. The first one is the enhancement type. So you can have a broken gap kind of a structure for both NMOS and PMOS, and there is an arrow. That arrow is going to tell you about whether it is N channel or P channel. You can look over there in this particular symbol. The arrow is pointing to the body bias, right? It is not on this source. It is on the body bias. So it is another symbol which is used in the literature. So this is body bias is towards the device. For N channel, it is outside of the device. So this body bias will be having the opposite arrow direction, whatever your source could have, right? Now this is the below symbol is N type. Here there is no broken line. There is no broken line over here. So this is your depletion type. Now let us understand how the band structure in silicon is going to work. Let's say you have a silicon material and it is actually N-type. N-type silicon you have. So in N-type silicon, what I told you, that the EF will go, it will move towards upside, right? So intrinsic energy level was this, which was somewhere in the middle of the band gap. This red color is the band gap, right? So it was somewhere in the middle of the band gap. But since it is N-type, so this EF is moving from here to here. This is moving, this is shifting, right? And this is contributing to the built-in potential that can be taken up from the equation KT by Q log here donors are there, so ND upon M9. That's the built-in potential seen in this particular device, because this is just one type. So this built-in potential existing over there, right? In N type only. If junction is there, then the built-in potential of P and built-in potential of N, both of together, and at the junction, that built-in potential actually is represented as NA into NB divided by NI square. So that's, and this KT by Q is nothing but the thermal potential, right? We represent it with VBI, built-in potential for N device, N most semiconductor, N type semiconductor. Now there is another definition of electron affinity and work function. What is electron affinity? Electron affinity means you can apply an energy to the electron sitting in the conduction band so that it can leave the conduction band forever and it can go to the vacuum level. Vacuum level is nothing but you are freeing the electron from the atomic structure of that particular material, right? So it is free from the material now. It will never come back, right? This is known as the electron affinity. And another thing is called as work function. So the work function is from Fermi level. You are going to apply the energy, and this energy is going to take it to the vacuum. That is the Fermi level. Work function. From Fermi level to the vacuum, you will be having. So this is what you will be having: the electron affinity plus EC minus EF. EC minus EF. So what we know that from here to here, this is what your EZ by 2, right? And then you have the built-in potential. So you can choose the EZ by 2 and built-in potential in order to figure out phi s in terms of J, EZ, and built-in potential. That formula will be working for the work function for all types of semiconductors. The work function can be modulated. How it can be modulated? For example, in this particular case, you are having N type. This is N-type material. So this is actually the Fermi level. And from here, you are going here. If I'm going to make it P-type, so P-type means my Fermi level is here, right? So the Fermi level is being shifted. It means my phi s, it has to start from here and it has to reach here. So in this fashion, you can modulate your work function of silicon. Okay. Work function for metals, because in metals, EF and EC, both of these are coincided, right? So electron affinity, whatever you have, that's the same as work function in that particular case. There is no difference in that. So let us understand for a particular PN junction, how it was. Let us revise that. So there were two regions, N and P. In both of these regions, the electrons from N side and holes from P side will actually recombine in this region, which is near to the junction. And we call that both of these will get diffused, leaving behind these fixed ions. These fixed ions were contributing to the electric field with the Poisson's equation, and that electric field is contributing to the potential. So this is the built-in potential. I discussed it earlier that we are having the lower potential towards P side and higher potential towards N side. So this is what the built-in potential, and this is contributing to your V gamma. That is the cutting potential of the diode, or like that. So similar kind of potential is existing when we are talking about MOSFET. So in the MOSFET, instead of the semiconductor junction, we are having a different kind of junction. So I told you how the band structure can be prepared, right? So first of all, we have metal. So let's say this is my conduction band and this is the electron affinity. Just a minute. Fine. So we have discussed this p-type and n-type junction when are combined together, we are having such built-in potential. And the similar kind of built-in potential is seen. We have also discussed the same thing for the heterojunction device. So for heterojunction device also we discussed that if there is a difference in the electron affinity, then we have to bring the vacuum level all together and then we have to go ahead. So same thing we will be applying for the MOSFET. If you remember, let me repeat for the heterojunction, we discussed the heterojunction device, PN junction, heterojunction we have discussed. So in that we have taken one N-type material which was having the wider band gap, and this was N-type was somewhere here, right? And it was having its vacuum level somewhere here, okay? And then we were having a P-type device. So this was the EF level. And the vacuum level was existing somewhere here. The vacuum level was somewhere here. So what we have to do in this, since the vacuum levels are differing, right? So at the boundary, what you have to do, you have to connect both of these. So the boundary should be continuous. Always remember the boundary is expected to be continuous. And in order to make that continuous, what you have to do, first of all, we have to match the EF. First of all, match the EF and then try to bring the boundary all together at continuous level. So when you are going to bring this EF all together, I'm representing it by a different color. So this is your new EF. This is your EV. This one is your EV. And this is, let's say, your EC. Now your whatever Fermi level to vacuum level was there, that is actually going somewhere. Let's say it is going somewhere here. Now, whatever difference, if something is seen, what you have to do, you have to connect it accordingly. Let's say this one is a little higher. So it means you have to bring it down at the A's. A little bit down it will come. And if it is coming a little bit down at the A's, you'll be having some such type of structure. Because here the conduction band is upside and this was the conduction band in this way. So it will go in this fashion. And this is how the complete band diagram will be prepared. And this was your EF level. You understood this? Please type in the chat box why if you understood this, so that I can proceed. We have already discussed this heterojunction PN junction. We have already discussed. If you understood this band diagram, please type in the chat box why. Why we are talking about this? Because if you want to do related research in this, then the band diagrams and whatever Professor Bulusu told, that derivation kind of things are very much necessary, and you should know all those things. Then only you can proceed in this. You should know how the electrons are changing the behavior, how the number of states are changing the behavior, how the band diagram is banding, and all these things. Yeah. So let's proceed to the next one. So the next one is the MOSFET energy band diagram structure. So in the MOSFET, we have MOS junction. This is M, then oxide, and then semiconductor. What I'm going to do, I'm taking it in this way. M, then O, and then S. So this is for metal. Next one is for oxide, and the third one is for semiconductor, right? Now you can see over here, this metal is having its EF over here. Semiconductor EF is somewhere here, that is aligned, and this actually Fermi level is also aligned, and all of these are having similar kind of vacuum. This is the vacuum level. Let's say it is completely fixed for all. If you are changing a little bit, material, if you are changing a little bit, let's say I'm using a metal which is having at the Fermi, when the Fermi levels are aligned, you are having the work function somewhere here. you might be knowing that the work functions are different. For example, silver is having a different work function, copper is having a different, and aluminum is having a different work function. Platinum, gold, everything is having a different work function. For N-type devices, generally the gate is taken approximately from 3.6 electron volt to 4.4 electron volt. Typically it is taken. This is the range for N-type device. For N-type gate metal, you will be taking the work function 3.6 electron volt to 4.4 electron volt. And for P-type, you will be taking this somewhere around 4.8 electron volt to 5.5 electron volt. You will be choosing for P-type. These are the typical values for N-type and P-type. Somewhere in this range, if you will be having, if you are not having in this range, then your threshold voltage is getting modulated drastically. Although in this range also your threshold voltage is getting modulated, but yes, still it is the suitable range. So if you are having the vacuum level over here, what you have to do? Your job is to bring the vacuum level at par. But since in the steady state condition, vacuum levels of both of these were at this stage. So it means what you are going to do, you are going to make it in this way. So basically it will go in this way. And then this complete, the conduction band complete will be going in this way. Okay, so the shape is actually modified. If you are having, let's say, the Fermi, the work function of this is more, in that case, it is going in this way. This is coming straight and then it is going this way. Whatever the vacuum level is there, other things have to follow because we have to rule for electron affinity, for work function and everything. So if it is coming in this way, you can see that it was coming from upside down. So what it is going to happen, it is taking it in this way. It is going to take it. In the previous case, it was taking the shape of this type. Okay, so let us understand how this type of shape, and if the shape of this EC or is changed, it means correspondingly the EV is also getting changed in this way or whatever side. So it means from EF you are deviating, your conduction band and valence band are deviating from its original position. So near the surface, this is the near the surface and this is away from the surface. Away from the surface is the steady state. You have the steady state which is away from the surface. So this away from the surface is the steady state. Steady state is constant, right? At the surface, you are being modulated. So here you can see that it is going away from this valence band is going away from EF. If it is going away from EF, what does it mean? It is more P-type or less P-type? Please type in the chat box. If the Fermi level is going away, as a layman, just understand like this. This is the EV and EC. And my Fermi level initially was, let's say, this line. And now I am drawing the other line, red line. Now this is going away from the previous Fermi level line. So it is moving more towards P-type or less towards P-type? Yes, please tell. This is red is the second case. This is moving away, right? So it is more P-type or less P-type? Yes, please answer. Can you hear me? Am I audible? More P-type. No, it is going to be less P-type. More P-type means what? See, initially, just have a look at this. Initially, what we have, our Fermi level was in the mid of it. So, and that was intrinsic Fermi level. So it is represented by EI also. Okay. Now you have EV valence band and EC conduction band over here. Now the thing is, if you are making it more towards, a little bit towards, let's say little bit towards this side. So from intrinsic, It means that was neither p type nor n type, right? So it means what? It means you are moving a little towards p type. Now I am making it more towards valence band. So it means what? It is moving more towards more p type. This is one condition and this is second condition. So it means this is more towards p type, more p type. Here we are increasing it towards this. It means it is more towards p type. In our case, what we did, we are moving it away from EV. So it means we are moving towards EI. EI was somewhere in mid between. So more closer towards EI means we are moving towards intrinsic type. Okay. So it means it is less p type now. I hope you understood it. Yeah, yeah. Okay, so it is less p type. Less p type means what? Let's say my body was having, the substrate was having, let's say 10 raised to power 15 atoms per centimeter cube. So moving towards EI with the help of whatever metal we have selected at the gate, it means what? I am reducing this concentration maybe 10 raised to power 30 atoms per centimeter cube. Means p-type concentration, right? Moving towards much more intrinsic. Intrinsic is what? 10 raised to power 10 atoms per centimeter cube. 1.5 into 10 raised to power 10. That was the intrinsic concentration, Ni. Okay. So this was the original substrate doping. So p-type holes in the substrate were these many. Now this is what? This is if I am modulating with the help of gate and my EF is going away from EV, it means I am making it less p-type. This is lesser than its origin. Let's say it is P1. So this P2 at the surface actually is lesser than P1. This is your P2. And we are moving more towards intrinsic type, right? So this is the case. So now let us understand the accumulation. What is the accumulation region? There are three regions of operation. One is, there are three regions based on how the gate voltage we are going to apply. First one is accumulation, depletion, and inversion. So accumulation, depletion, and inversion. Accumulation means you are trying to accumulate whatever type of charge carriers were available in the substrate. Whatever charge carriers were available in the substrate, we are going to accumulate those near the surface. Surface means we are seeing the junction of oxide and N channel. That interface is called as substrate. Surface. We'll be taking a cut just 1 nanometer below this. This red line is a cut. You can give the name A dash. Much more details about this will be covered in our next advanced semiconductor related FDP, which is scheduled in June, maybe second week. So those who are really interested, they can register for that. Registrations are open for that. So you'll be taking a cut for this and then you will be having it. So here, just to understand, see, we are going to accumulate. So it means we have to apply the negative gate voltage. So I'm taking a little lesser so that we can cover this MOSFET part a little bit at little bit faster speed. Okay, so we are increasing the gate voltage. It means increasing the gate voltage. How the energy band diagrams will go. So increasing in negative side. So gate voltage also negative side. So the energy becomes positive. So energy is going up. If the energy is going up, it means the vacuum level is also shifted upside, right? Energy, I'm going to apply the negative gate voltage so that I can accumulate the similar negative gate is going to attract positive on the second plate. This MOS structure is somewhat like that. This is metal, then oxide means this is oxide insulation, and semiconductor is also a kind of metal. Can I say that this becomes MOS capacitor? This is a capacitor. So in capacitor, we know if I am applying positive over here, positive voltage, It means on this plate, negative charges are attracted. If I am applying negative over here, it means another plate, positive charges are being attracted. So the same phenomena is going to happen over here. You are going to apply something at your gate voltage, and the opposite polarity of that is going to be attracted on the surface just beneath the insulating layer. Okay, that's the thing. So just remember that thing, and then let's proceed. So we are going to apply negative voltage over here. So here the positive charges are getting accumulated, these positive charges. So you will represent in the diagram like this. But in order to understand from the energy band diagrams, that is very much needed for the researchers who are working in the devices, right? This you can make understand your BTech first year, second year students, that is good. But for final year, if you are having some subject, you have to follow this approach so that they can understand. Energy band diagram approach you have to understand. Yeah, so what you are going to do is you are going to apply a negative gate voltage that is kicking up the energy band diagrams upside. So the vacuum level is also shifted upside. If the vacuum level is shifted upside, what you are going to do is you are going to take a straight line, and then this was the vacuum level for silicon. Right. Now, since you came from this to this way, this has to follow the continuity. So it means it is going to be at the junction, it is going to be upside, right? This EC is going to be upside, EV is also going to be upside, and EF was originally like this. So if EF was originally like this, EF was originally like this. So means what we made, you can see EF is much closer to your P. So some of the states of P are there. It means more holes are available. EF is near to P means holes are available. EF near to EC means EF near to EV. EF near to valence band means ample holes are available. EF near to EC, conduction band, means more electrons are available. So here you can see EF is much more nearer to your EV. It means the holes are available. Look at this, holes are available, right? So holes are positively charged particles. So that's what we'll be calling, that positively charged particles are being accumulated at the surface. And that's what we call this as accumulation region. Next one is actually the depletion region. Depletion region means the channel is depleted from all type of charge carriers. So EF is actually somewhere in the middle of it, middle of your it is not occupying any EC or EV states. That's the thing. So for that, what you have to do, you are going to reduce the VGS. So first of all, when VGS was 0, this was having, the channel was having some charge carriers which were p-type. What we need to do, we have to repel those charge carriers. So in order to repel those charge carriers, VG we need to apply positive. This positive is repelling those charge carriers away and is trying to attract the negatively charged particles. Those are electrons. Movable particles are electrons. So it is going to attract those. But this is going to take a while. So positively applying VGS slowly is making this particular region depleted of the charge carriers. Depleted means these are away from the surface. All charge carriers, positive or negative, are away from the surface. So it means you have to reduce. Positively means QV will be negative. Negatively means you have to bring it down. Energy band diagrams, you have to bring it down. So bringing down means it is going to impact in this way. Your vacuum level is somewhere here, and the vacuum level of this was somewhere here. What you have to do, you have to connect it in this way, right? And that's what it is going to take, this kind of shape. And at this, it has to prepare the continuity, and that's what it is bringing down in this way. And you can see your EF level is not touching your conduction level. This is your EF level, red line is your EF level, and this EC level is away from this. So it means this is your depleted of the charge carriers. So although it should come exactly in the mid of it, that means it is the depletion region. The next region is the inversion region. Inversion region we will be calling whatever the number of charge carriers we have dropped p type in the substrate, just opposite of that should get uh, attracted in the channel region at the surface, so that we can call that this is the inversion region. So in inversion region, what we are going to do is we are applying much more VGS, more positive. More positive means it is coming more down, right? If it is coming more down means this is much more sharper. If it is much more sharper, it means what? This is coming much more down. This is coming much more down. If it is coming much more down, just look at this. This is coming in this way. It means much more charge carriers are trapped, which are electrons, right? It is much more n-type, so much more charge carriers, electrons are trapped, and that's how this is inversion fiber. So that I have taken. See, this was your MOSFET, right? Here there are two things. One, you have to take this type this way. Another one you have to take this way. And both of these energy band diagrams are going to tell you that what type of charges is being developed. See, vertical line is going to tell whether the inversion is going to happen or not, from accumulation, depletion, and inversion, where we are moving in any of those regions. And this horizontal line, let me change the color of the horizontal line. This horizontal line is responsible for the current conduction, and the vertical line energy band diagrams are responsible for the control of the channel. And horizontal line is responsible for the electric field, how the electric field can flow. So once we have done the control related things like from depletion, accumulation, and the inversion, now we have to move towards the electric field related things, which are responsible to move it from move the electrons from source to the drain. So it is about this. See, we know that in NMOS you have N-type. Here this is N-type. Then in middle it was P-type, and then because it was a substrate, right? N-type heavily doped, P-type is moderately doped. I'm going to take now for the IV characteristics, how the drain can control, we have to take such type of cut. In the previous case, such type of cut was taken that was contributing to MOS. First of all M, then O, and then S. Now we are going to discuss this NPN. So N means, first of all, let me draw. N means your Fermi is somewhere here. And P means, so the Fermi level has to be aligned. First of all, this is aligned, the Fermi level is aligned. And P means it is much more near to this. So it was lightly doped, so I am taking it a little away, right? Now what you have to do? You have to make it smooth over here. So this is the unbiased lateral energy band diagram for PMOS. Unbiased lateral energy band diagram for PMOS, NMOS I have created. So now what you can see if an electron wants to come from here to here, it cannot move because it sees a barrier width that is equal to the channel and a barrier height. This is the barrier height, right? It is also seen. So barrier width and barrier height are good enough. So the electron cannot travel from source to the drain. That we have already discussed in our Zener tunneling, right? So the width is also more and height is also more. We cannot reduce the width because physically whatever gate length is there, we are not able to reduce that, right? In the Zener, there were no physical control. So the width is being controlled by the reverse bias, right? But here the width is actually underneath the gate. So we are not able to control it. And the height we can control. How we can control the height? So we are going to modulate. We can apply the gate voltage in this particular region So this barrier height is being reduced. That is one way. Now, even though barrier height is actually reduced, then also if the same level is there, you can think of, let's say, there is a water tank. Okay. So water tank means this is N side, this is also N side. And the next one, the middle one is P side. You are going to modulate the P side. Let's say this is your P side. You have modulated it and you brought it down. But the drain, you have not applied anything. So all of these are at same level. If it was a water tank this way and this way, can we expect that the water is going to flow? No, we can't expect. The water will flow if you are having this a little lesser as compared to the source. So it means you have to apply the drain voltage, right? So you have to apply the drain voltage. So this energy band diagram, whatever I am going to show over here, you can see over here, this is your EC, EB, sources there. Here we have applied some drain voltage, but red color shows that the gate voltage is 0, right? So even though I have applied some drain voltage, so from this level, I was able to move it to downside. But when the electron coming from here sees that there is a barrier height, this barrier height it cannot. And along with this barrier height, it is having good amount of width as well. So it cannot actually move. This electron is not having the good enough energy to cross this barrier width and height. So what we are going to do, we have changed the VGS is equal to 0.75 volt. After changing that, what we are having to do is we have reduced this height, we have reduced. Now width is same, but the height is reduced. This reduced height is allowing this electron to go and come over here because the level of this is lesser than the source level. The conduction band of source is at the higher level and the conduction band of the drain is at the lower level. So the electrons are free to come from conduction band of this to the conduction band of drain. And that's how the current is going to flow. So this is the electric field which is responsible to bring these electrons forcefully from this to this. What is electric field? E is equal to dB by dx. So if we consider that, let's say L is the channel length from here to here, L is the channel length and VDS is the voltage applied. So since this is N type, this is also N type. So can I consider that the N type will be having negligibly small resistance? So whatever voltage you were applying at a drain or source, that is basically appearing at the channel. So VDS is appearing over here and 0 towards the source side, grounded, right? That is appearing over here. And this basically is applied across this channel length, that is LG. So how much electric field is created? This much of electric field is created. And this electric field is actually force on the electrons. What is the formula for the force in terms of electric field? Can you type in the chat box? What is the formula for the force in terms of electric field? So force is Q into E, right? So Q into E is actually the force applied on these electrons, and these electrons are moving. That's how the current is flowing. Now this current flow formula is understood. Now we will take the next part. So before next part, if you have any questions so far, please feel free to ask. Otherwise, we'll take a 5 minutes break and after that we'll come back. So if you have any questions, type in the chat box. Otherwise, type N in the chat box if you do not have any questions. Type N in the chat box if you do not have any questions or if you want some topic to be actually repeated. Especially, this is really good to understand the MOSFET device physics. If you understand the physics behind, then it is easy to handle with the devices, to work with the devices. Shall we proceed for the break? Type yes if you want. Am I audible? Type Y in the chat box if I am audible. Okay. So let us have a 5 minutes break and let's come back at 12:08. Okay. So let's meet at 12:08 and we will continue the IV characteristics of MOSFET. Okay, so let's come back after 5 minutes. Thank you. Please type Y in the chat box if I'm audible. Am I audible? Okay, thank you. Thank you. Thank you. So let's start it now. Yeah. So we have covered the horizontal x-axis and y-axis energy band diagrams, how these are controlling the flow of electrons or holes from source to drain. So this is what the characteristics will be defined by the energy band diagrams. Now the same thing is actually in terms of equations, we have to make it. Equations we are making, we call this as physics based analytical modeling. Equations are very much needed in order to give it to someone. Okay, you have a device where it is going to work. So if equations are there, it is easy for us to solve because we have some formula to deal with, right? Mathematically, we can solve that and it is going to be a great result, especially for the circuits, right? So what are the different things which are going to affect the IV characteristics of the MOSFET? First of all, there is threshold voltage. Threshold voltage is what? Threshold voltage is basically is the main minimum gate voltage after which the device is considered to be on. Means the sufficient amount of current is going to flow through the channel after the threshold voltage. So it is a minimum gate voltage. You can say the minimum gate voltage required to create the immersion layer for the channel. That is the threshold voltage. What do we mean by immersion layer? If you just look at this, just have a look at this. Yeah, this EC and this EC, there is a small difference between two. What does it mean? This small difference, vertical difference, says that the EC is still a little higher. So it is somewhat like this. We are having the staircases, right? So we have the energy to go from this to this. Likewise, these electrons can have the energy to move from this to this, and that energy is actually coming from this electric field we have been applying across this, right? So this energy, how, for example, let's say there is a small child and I am on the third stair, right? I'm asking, okay, come here, I'll give you a chocolate. Okay, so what he is going to do, he is taking all the steps, step by step, he is coming, right? He is coming step by step. But instead of this, if I am having the stairs in this way, that this, instead of these many stairs, the stair is somewhat like this. I am on the roof of one story. And I'm saying, okay, I have a chocolate for you, please come. So he cannot jump, he cannot fly, he is not Rajnikant, right? He cannot come. Whatever thing you can give, plate, pizza, burger, hey, he is not going to come because he is not having that much capability. Okay, so if only small energy is needed, that energy actually there is an attraction force because of the electric field, and these electrons can take cross that barrier, and that barrier height can be tackled by these electrons, and that's how the flow of electrons is going to happen. So what we need to do, if you look at this energy band diagrams closely, so it means this is having more electrons and this is having a little less electrons. So it means a bridge is being created. So this bridge with lesser number of electrons, because this is the source of electrons. So more electrons are available. These electrons are going through this bridge and then these are going to this. Yes. So this is going to help to understand what VTH can be. So VTH is there to create the inversion channel. Inversion channel means it is kind of a bridge of electrons so that from source to drain, the electrons can move freely. And the bridge is expected to be strong enough so that, for example, I have a bridge and it is having the capacity that one man at a time can go. So it means multiple people cannot move altogether. Otherwise, the bridge might be broken or something. Likewise, if you are preparing a bridge from source to drain, that has to be strong enough that multiple electrons can travel from source to drain. It means the good amount of current is going to flow, right? So we are having the threshold voltage, and this threshold voltage guarantees that the channel is having the good bridge of electrons. And multiple electrons can travel all together from source to drain so that the current flow is going to happen. Now, what are different parameters which are actually responsible to contribute to VTH? So first parameter is phi GC. Phi GC is the work function difference between the gate and channel. You can say metallic gate and the semiconductor, which is there in the channel. Minus twice of phi s. Phi f is the built-in potential. I told you phi f is equal to kT by q. That is Vt. Okay, Vt I am representing here by the threshold voltage. So I have to take another parameter. Let me take it kT by q. kT by q log of nd by Na upon Ni. Na upon Ni. I told you that for towards the p side it is rising from 0 onwards, right? And for n side it is positive. So it means this is actually taken negative over here. So twice of that it is taken. The reason being we just need to create this phi f is responsible for some holes. We have to create equal and opposite amount electrons. That's what we are taking, just double of that. Okay, just double of that is taken because equal and opposite amount of carriers means whatever number of holes are there, the same number of electrons we are going to create at VTH. That's what we have taken twice of phi s. There was difference in the Fermi levels. So this phi GC, work function difference was there. So this phi GC is coming from there. Then there can be some oxide charges available. So those oxide charges in at the interface in the oxides, there can be some charges. So for that I have Q ox upon C ox. There is the formula Q is equal to Cv, right? So C is what? The MOS structure oxide, COX, we will be representing that, and the charge inside that oxide layer is OX. So that is also contributing, that is opposing the charge attraction. So we have to counter that also. So minus QOX upon COX coming from there. If in bulk some impurities are there, so those impurities are also opposing. So minus QBO upon COX is coming from there. And then this is the excess one, B minus QBO upon COX. And this is represented by VTO minus QB minus QBO. B stands for body or the substrate. So if you are applying something at the body, at the substrate, that means that is also going to modulate your threshold voltage. So this is the actual threshold voltage and this is the modulated threshold voltage, right? And how this can be modulated? So this is modulated with the help of the potential applied at the substrate. You can see over here, this is source to body. VSB is source to body voltage. So if you are changing this, it means this QV is getting changed and definitely you will be having a different yeah, sorry, I got a call. It's working. So this VSB is responsible to tune your VTH, the threshold voltage. So you can combinedly, you can represent your VT, generalized formula for VT is VT0 plus gamma into root of minus twice of FB, twice of phi F plus VSB mode of it, because this is going to come negative, and mode of twice of phi F, because phi F is negative, so we are going to take mode of that. For P type, we will get it negative, where gamma is the substrate bias body effect coefficient. It means your VSB is changing your VTH. How it is changing? You can understand it from this diagram. This is my body, right? So I am, let's say, applying some positive voltage over here. What is the job of this positive voltage? This positive voltage is trying to attract the electrons. So if this is going to trying to attract the electrons, it means these electrons are facing. These were facing, this was trying to attract the electrons upside. But this is trying to attract the electrons downside. It means your VTH is getting modulated. VTH is the gate voltage when you are able to create good number of electrons in the channel. So basically, changing this voltage is changing your electron concentration at the surface, and that's what it is, changing all the VTH. Now let us derive the IV characteristics for the MOSFET. For that, what you have to take is just take such type of MOS device. In this, we'll take into consideration the simple model. We will just apply how the current is going to flow. So basically, we know that if there is QY charge trapped inside this, this is Y direction, Y axis. Okay, length of this channel is 0 to L. So at any place you have QY charge. This QY charge into W. W is inside this. See, this is the length. So this is L, and W is inside width of the gate. So this QY at any point, which is given per unit length into W, is the total charge into Vy. Vy is the velocity of these charges. Okay. So if we are multiplying these, it means we are getting the current. What is ID current? The drain current will be just opposite of this, right? Because charge are negatively charged particles. So that's what its direction is, negative. Vy is what? Vy is the drift velocity of the carriers. So we already considered that this Vy drift velocity, Vd formula, if you can recall, that was mu into E. So Vy is equal to mu n into Ey, right? Mu n into Ey. So this becomes mu n into dV by dy. dV is nothing but the drain voltage. You can write it dV by dy. This is dV by dy. That's nothing but the drain voltage. Or let's say it is not drain voltage, because at any point of y we are going to discuss. So take it Vy instead of Vy. So we can say that the voltage of the drain is actually having dropped in these parallel resistance paths. Let us consider that the complete 0 to L length has been divided into n similar length size channel. Okay, so every one of these will be having a drop in the VD. So the complete VD is divided into these n parts, right? So with the help of that, we have to find out Q and Y. Q and Y will be what? Q is equal to CV. We know this. So Q and Y is equal to C into V. How much V will be seen over here? So the over voltage VGS minus VT, that's contributing, along with the drain voltage that was minus Vy. At any point of time, that is minus Vy. So this is a simple formula. Q is equal to CV. We'll be taking that into consideration, and that's what now we are proceeding. Now ID becomes W mu n Cux, VGS minus Vy minus Vt, and dy by dx, dvy by dy. In order to find out the drain and voltage relationship, just integrate it. When you will be integrating it, you'll be getting, take y towards this way and integrate. VGS is constant, only Vy is changing from 0 to VDD, because, and this y is going to change from 0 to L. So you will be having this expression. This expression is nothing but your current in the linear mode of operation or in the triode mode of operation. Why we call that this is the current in the linear mode of operation? Linear, this is equation of line. Why this is the equation of line? Mostly, if you look at this in your IV characteristics, it will give you some such type of behavior, right? So this is kind of equation of line. This is kind of equation of line. This is the straight line. You can approximate it with straight line. This was your VDS. This was your ID. So we call this as equation of line, and this equation of line is governed by this equation. So this is only applicable when VGS minus VT and VDS are having governed by this equation. Inequality, this inequality, VDS is lesser than the over voltage VGS minus VT. Then this equation is valid. So that says that VDS is small enough. If VDS is small enough, then this quantity, which is nothing but VDS square by 2, that becomes a little lesser because VDS was smaller. So that's contributing lesser. So another thing is there are three regions of operation for MOSFET. First one is the cutoff region, then linear or the triode region, and the saturation region. So we have discussed the linear region of operation. What is the cutoff region? If you do not have VGS is lesser than VTH for NMOS, you have not reached to your VTH. In that case, your channel is not formed. If the channel is not formed, it means the electrons cannot move from source to drain. If the electrons cannot move from source to drain, it means what? No current can flow. So in the cutoff mode, you'll be having ID is equal to 0 in the cutoff mode, right? ID is equal to 0 in the cutoff mode. So another one is the linear region. In the linear region, the current equation is governed by whatever equation is expressed over here, this one. And next one is the saturation region. So let us discuss the saturation now. So in the saturation, you are going to have VD saturated is equal to VGS minus VT. Means your VDS has reached to good enough value that it is equal to VGS minus VT. So basically, increase in EY is compensated by decreasing QN. So it means your ID is being saturated when QN equals to 0 at the drain. So it means a triangular shape. This type of shape you will be seeing when you are increasing your VDS. You're increasing your VDS. So what is going to happen? Your increase in EY is going to happen, and that is being compensated by decrease in QN. So the QN at the drain is actually, you can see it is depleted from the charge carriers. So from here to here, these are actually drifting all together. These are not drifting. These are actually coming all together, crossing this barrier. Convection kind of thing is going to happen. Fine. So in this case, VDS is increasing, channel length is, effective channel length is decreasing, and ID is increasing. So how it will be working? It is working in this way. ID is proportional to 1 upon L minus delta L, because from this formula, VDS is increasing, effective channel length. You can see effective channel is still here. It is reduced. You increase the VDS, so the effective channel is reduced, right? Initially, if the length was L, so now it is L minus delta L. Okay. So if it is reduced, it means 1 upon L minus delta L, ID is proportional to that. So if you are taking the binomial theory into consideration, you are having 1 by L into 1 plus delta L by L, because the other terms delta L by L square, cube and all those will be negligibly small. So we can neglect those terms. So instead of just 1 by L, we will be replacing in our formula this value. What it is going to give us? This is going to give us this value. ID saturated is equal to mu n Gx W by L by 2 VGS minus VT whole square. That's the layman formula. But taking channel length into consideration, we will be having 1 plus lambda VDS minus VD saturated. This is the formula for the saturation mode of operation. Any questions so far? If you have any questions so far in this, please feel free to ask. Do you have any questions in this? Please type Y question in the chat box or N in the chat box. If you don't have any question, please type N in the chat box. No questions? Okay. So let's proceed now. So we got three regions of operation, and those three regions of operation we found how it is going to work. Now let us draw the IV characteristics. So for all three regions of operation, these will be the IV characteristics, right? And these IV characteristics, you can see the left hand side is actually the input gate voltage and drain current. How the gate is controlling the drain. So it is similar to your diode IV characteristics. It is similar to this. It is going in this way. After VTH, your current is being increased. Kind of exponential increase is there, right? So you will be taking VDS constant and then you will be changing your VGS. You will be observing what is the drain current and you will be having such thing. We have, this is called as the transfer characteristics and this is the output characteristics. While in case of BJT, you have input characteristics also. We do not have input characteristics in this. Can we have VGS versus IG? What will be the IG current in case of MOSFET? What will be the IG current? Can anybody tell? The gate current in case of MOSFET, how much it can be? That's what it will become input characteristics. If I am drawing the input voltage versus the input current. So the input current, the gate current is 0. Why it is 0? Because we have a good insulator which is stopping all the carriers going inside the device. That's what it has, the electrical insulation at the gate, at the input level. And that's what its input impedance is extremely high, right? For all the MOSFET devices, your input impedance is going to shoot up. And that's what, as compared to your VCT, it is much more useful because it is not going to give you the loading effect on other devices. Whatever the devices were there, it is not going to give you the loading effect on that. So basically, we will be not having the input characteristics, but only transfer characteristics will be having. Then we have output characteristics. So how the output characteristics will go? There are all three regions of operation in this way. This is the cutoff region, this is the linear region, and this is the saturation region. So this linear region is also known as the ohmic region. And this kind of parabola you are going to have, this is nothing but your pinch off voltage locus. This dotted line is your pinch off voltage locus. So with this, if you are increasing your VGS, you will be getting all these different curves, right? You'll be getting all these different curves. So if I want to find out the operating point of my MOSFET, which is getting connected, drain is connected to, let's say, some resistance. So it means the similar formula, whatever yesterday we have done, we will be using that, right? And then we will be finding out that what was my VGS and what was my VDS along with that straight line, because that straight line is because of the resistance, ohmic line, right? And these can be the operating points. This can be one operating point that is bringing it to the linear mode. This is bringing into saturation, saturation. Till here it is saturation, and after that it comes into the cutoff mode also. So likewise, we will be finding out the operating points or the Q point. So it is summarized over here, the various regions of operation and what will be the corresponding equation. ID is equal to W by L mu n CX VGS minus VTH minus VDS by 2 into VDS. This is the formula. And the same formula, what you can do, just learn the triode formula. And if your VDS is greater than VGS minus VTH, just replace that value of VDS in your this formula only, and you will get the second current also. Because after that corner where VDS is equal to VGS minus VTH, the current becomes constant, right? So you will be getting this formula and just multiply this. That is the body, channel length modulation coefficient, lambda m. That's the channel length modulation coefficient. So just learn this one and then just multiply this by replacing VDS is equal to VGS minus VTH in the triode mode equation. And you will be getting this equation. Yes? Any confusion so far? Any questions so far? No questions. Okay. Fine. So this is the channel length modulation. It happened because when you are reaching in the saturation, your charge has been depleted. Why it is depleted? This is your N plus region. You are giving positive over here. So basically it is being reversed bias, right? This was P type. So this is PN junction reverse bias. So reverse bias means this depletion is going to widen, widen and widen. So more the drain voltage you are going to apply, it is going to be widen, widen, widen. And after a particular point of time, it is also repelling this portion. So that's what it is going to take the triangular shape. So once the electrons are going to reach over here, after that the electrons are having very high speed and then these are reaching towards the drain side. What will be the effect of this in the IV characteristics? You can have a look at this. So L is very, very greater than delta L, and without the channel length modulation, it was expected to be constant. But with channel length modulation, you can see it is a little bit increasing. Slowly it's increasing, right? So that's what the IV characteristics of the MOSFET you are able to see. Now, very important, people get confused and even students also get confused. You might also have faced maybe first time. There is a difference between MOSFET and BJT IV characteristics. Generally, we used to say, okay, generally common source configuration is much more familiar for MOSFET. And for BJT, common equivalent is what? Common emitter configuration. Emitter means that is having ample number of charges. Source means ample number of charges. Collector means from that emitter, collector is going to collect those charges. Drain means from source it is going to collect the charges. So the similarity is emitter and source, collector and drain. Okay. And gate and base, these are actually modulating the characteristics. So basically, we generally get confused in the saturation mode because the MOSFET or BJT, these can work like the digital device, digital binary device like 0 and 1, or maybe like in analog devices like an amplifier. So in order to make it an amplifier, where you have to bias is, you have to bias always in this region. Always in this region it has to be biased, right? And this region of operation in case of MOSFET, just have a look. In case of MOSFET, it is saturation. But in case of BJT, please make a note of it. It is active mode of operation. We call this as active mode of operation in case of BJT. While in case of MOSFET, we call this as saturation region. So we have to use the saturation region of the MOSFET as an amplifier, while for BJT, we have to use the active mode of operation to work the device like an amplifier. Where is the saturation for BJT? Look at this. Whatever triode region we are seeing, that is nothing but the saturation region in BJT. While this region is known as the triode or ohmic region in case of MOSFET. And the cutoff region, of course, that's the same. Cutoff region is same. There is no linear or ohmic region in BJT. MOSFET is having the saturation region, BJT is having the saturation region, but that saturation region phenomena and the terminology is different. How it is different? In case of MOSFET, you are saying that the saturation means the current is being saturated. The current is constant. Although this is not constant, a small increment is seen because of the channel length modulation. So the saturation phenomena comes from here, that it's been enough. Now the current is not going to increase. While in case of BJT, the saturation comes from where? Saturation says that both of the junctions in the forward bias, there is emitter EB junction and BC junction. We are saying that in cutoff mode, both of the junctions are in reverse bias. In saturation region, both of the junctions are in forward bias. And what is in active mode of operation? Can you please tell me, in active mode of BJT, what we are having? Which junction is forward and which one is in reverse bias? EB junction is forward or reverse bias? So EB junction in forward bias in case of BJT, and BC junction is in reverse bias to make it work like the active mode of operation. Okay, active mode of operation is used for the analog applications like transistor as an amplifier, and for digital applications we'll be using the saturation mode and cutoff mode. While for BJT, MOSFET will be using the saturation mode of operation in the analog domain for amplification purpose, while the cutoff and linear mode will be using for the digital applications. So cutoff means the device is off and ohmic region means the device is on. That's equivalent to cutoff and saturation in BJT, right? So this gives you device on-off condition, which only is required in your digital applications. So now let us come to the CMOS. So what is CMOS? CMOS is the complementary metal oxide semiconductor. CMOS is complementary metal oxide semiconductor. What does it mean? This is a kind of technology, like we have different kinds of technology in order to prepare the multiple digital devices. You might have gone through few of them, maybe RTL, DTL, TTL, etc. etc. Okay, fast transistor logics, transmission gate based logics, and all. So in CMOS, we have to make sure that the number of NMOS and PMOS is same. NMOS and number of PMOS are same to implement any logic. That is what the CMOS is. Now, why it is required? So if you look into DTL, TTL, RTL, etc., maybe register based, most logic operations are also there. In all those, there was no symmetricity, and fabrication was actually not easy, because if you are putting a resistor or maybe something else, maybe diode at some time, so to prepare that was actually a different pattern, different phenomenon. So CMOS is going to give you the ease of operation, and on the top of everything, you are having one p-type body. On that, the same body you can grow p-type and n-type in the same substrate. So it is going to give you the compact chip. The area is reduced and the packaging can be done easily. As contrary to this, BJT based systems, what you have to do, there is NPN transistor. You have to make sure that all of these three regions are encapsulated so that one device is not going to be grown on single substrate, just like your MOSFET. On MOSFET, you can have a single substrate and then you can grow whatever devices you want to grow. So in this case, in the CMOS, you are going to take first of all a p-type substrate. On the p-type substrate, you are going to diffuse N plus region and P plus region. Before that, you will be defining where your gate is going to come. Defining that will be done with the help of photolithography. So you are having the oxide grown over here, the insulator. After that, you will be defining your these regions of operation. So using the photolithography, you will create your patterning, and then diffusion or ion implantation will be done in order to grow these N plus regions. Once these are done, you will be preparing these metallic contacts all over source, drain, and gate, and your this device is completed. Now these are actually for the isolation purpose. You have to shield this device. You have to shield this device so that there is no cross correlation with the other nearby devices. So these are the trench isolations you have to put. Thick isolators are there. Okay, these are a little bit deeper also. Now you have to create PMOS. So for PMOS, you need N type of substrate. So N well is created first of all. This N well is working like the N type substrate for the PMOS device locally. Then you will be having the gate oxide to be grown, and these are photolithographically patterned. And after that, the diffusion takes place to grow the P plus regions, source and drain, and then the gate, metal, and other contacts are created. So this is how your CMOS is fabricated. And yes, we have discussed the benefits of CMOS. And this is the analogy. As I told you earlier, there is a water tank that is equivalent to source. This is equivalent to gate, and this is equivalent to drain. So it is having good amount of water. The water, with the help of this control valve, is coming to the drain, and these water particles are equivalent to your electrons. So MOSFET applications can be MOSFET can work like a switch, and it can work like an amplifier. I have taken this very simple example. So let me finish it very fast. If I am going to apply 0 over here, this is NMOS device. So what is VGS? VGS is 0. It means it is lesser than VTH. So which mode of operation it will be? Cutoff mode. Cutoff mode means this is kind of not connected, electrically not connected. If it is not connected, this is my VS, and current can only flow if there is a closed path, but there is no closed path. If there is no closed path, so IDS is 0. So what is IDS into RD? That is also 0. So it means your VS is directly appearing at your VO. Whatever the power supply is there, that is, you can put it VD. So that VD is directly appearing at the output. Let's say this is VD. This is appearing at your output. So it means you are applying 0 against that 0. Your input is 0 and output is high voltage. VD is considered to be high voltage. Now let's apply VD. Input is VD. So if I'm going to apply VD over here, so VDS. Now VDS minus VD. That's good enough. That's very, very good enough, right? So if this is good enough, it means good amount of current is going to flow, right? But at the same time, good amount of current is going to flow. It means there is some drop over here. So definitely the VDS is very less. Good amount of current is flowing. There is only one path for the current. This is the path. Good amount of current is flowing. It means much more portion of your VS is getting dropped across RD. So what will be your output? Output is much lesser. So what is your VDS? VDS can be actually represented by VDS is your VO only, right? This is your VO only. VDS is equal to VO, and that is VS, or let's say whatever you call this, VD minus ID into RD. ID into RD was good enough. So VDS you are getting lesser, very less. So this is linear mode of operation, right? And VDS is very less, so you will be having VO near to 0. Means low. It's not 0 in this particular case, but yes, it is low value, right? So in this way, it is going to work like a digital device, like a switch. When 0 was there, the output was 1. When 1 was there, VD is equal to 1. 1 and 0 are actually the logical values. So in electrical, we have certain value in place of 1 that can be current or voltage. For example, here we are talking about voltage. So let's say 5 volt we are saying that is equal to the high value. So 0 means it is equivalent to the logical value 0, and 1 means it is the logical value whatever the voltage VDD or VCC voltage is there. That is your one value or high logical value, right? Now, if I want that my device should work like an amplifier, amplifier means I have to give some volt signal at the input and it should get amplified. Okay. So for that, first of all, I have to make sure that my device is working in the saturation mode of operation. So saturation mode of operation means first of all my VGS or VI is expected to be greater than VTH. That's threshold voltage. And I have to make it a little bit more beyond that. After that, I will be superimposing this sinusoidal waveform and I will be seeing that my sinusoidal waveform is getting amplified. Okay. So that we will take the MOSFET as an amplifier. Will be taking a lab related to that on Friday, coming maybe 1 hour or so. So this I have briefed you about how the MOSFET device can work, like a simple a simple switch or simple amplifier, how it can work. So a little bit more about MOSFET is listed in this slide. Punch through means punch through means your gate control is completely lost. Another thing is pinch off means you have started pinch off. Pinch means this was the drain. So you have entered in the pinch off. Pinch means kind of pinch the beak kind of at this drain place has happened because the carriers have aligned in this way because of the drain reverse bias, right? So this is the pinch off channel length. It is responsible the start of channel length modulation. Another thing is drain induced barrier lowering. Drain induced barrier lowering means if you are increasing the drain and the gate length is very small, then instead of just lowering the barrier height with the help of gate control, your drain is responsible to reduce the height. So that is drain induced barrier lowering. That is not good for the health of the device. There is subthreshold swing, which you should always remember, that is 60 millivolt per decade at room temperature. And the static power is more at lower technology node as compared to the dynamic power because the gate length is very small. And if gate length is small, it means the control is less and you are not able to control that much electrons in the off state also. Okay. And there is something called as technology node. That is, previously it was taken as the technology node is actually your gate length. But technology node, nowadays it is no more gate length. It is the smallest feature size. That can be like 10 nanometer, 5 nanometer, 1 nanometer, and somewhat like that. So stable, since few years, stable technology nodes are 10 nanometer, 12 nanometer, and 28 nanometer. Below 28 nanometer, 22 nanometer, you have FinFET. Instead of MOSFET, you have FinFET below 22 nanometer. Okay. FinFET is just like your MOSFET only. These are the advanced devices. Those who are interested to know more about FinFET, tunnel FET, gate all around FET, and all these things, you can register for our upcoming FDP with it, which is with the same title, and we will be covering the advanced topics of this. Okay. So commercially available 10, 22, and 28, these are stable things. But at the same time, many of the companies are approaching to make the commercial 1 nanometer, 2 nanometer, and 3 nanometers. These are in production, so soon these will be there in the market. So if you have any questions so far, please type in the chat box. If you don't have any question, then you may type N in the chat box so that we can conclude the session. And the next session will be at 5 p.m. today. Subthreshold swing and subthreshold slope. Yes, okay. So subthreshold slope is the slope. That's the same. But let me tell you what's the literal meaning of it. You have some such type of characteristics, right? On the log scale. We are talking on the log scale. Okay. So on this scale it is V and on this scale it is I. So subthreshold swing is taken by taking d by dv. Sorry, first of all you have to take it in log scale. Look at this. This is 50 millivolt per decade. Per decade is the current. So you will be taking log of I over here, right? 60 millivolt per decade. So you are getting change in V and the corresponding change in log scale I. Log scale I. So that's what from here it is known as swing. We'll be calling this as swing, subthreshold swing. But it is nothing but if you look at this, this is the formula dv by dx. That's the formula for dy by dx. That is the slope of any line. It is kind of line, right? It is kind of line. On log scale, it will be the threshold starts from here, right? So this will look like linear. This is VGS and this is your ID. So this is the below cutoff. So on linear scale, if I can draw it, so on linear scale, it will look like this. So linear scale on the log scale will turn into the saturation, right? That's what we are having it somewhat like this. And before this, this is not looking very good because let's say we are going to start from 10 to the power minus 12 to we are reaching somewhere 10 to the power minus 7. So this is on linear scale, it is very less. It will come all zeros, right? So we are not able to visualize on linear scale. So what we are, let's say, right hand side is the linear scale, right? So basically, this log scale is going to help us to figure out that how much the device is good for the static leakage. We have to minimize that leakage. Okay, for the idealistic device, the device should get turned on. Let me change the color. It should turn on in this way. It should turn on in this way. But it means if it is going to turn on in this way, it means this is the slope, right? This was the slope, right? So it means this slope we are going to change. We are going to reduce this slope. If we can reduce this slope, it means the device is more towards this type. It is more towards this. Okay. Reducing y, we are saying this is 90 degree, complete 90 degree, right? But if you look at the formula, it is dv by d log of I. So v is not changing at all. I is drastically changing. So if v is not changing at all, it means I am going towards zero direction. Right? That's what we'll be calling that lesser the subthreshold swing or subthreshold slope is better for our devices. Anjana Bhardwaj, am I clear? You understood this, Anjana? Okay. Any more question? Please feel free to type in the chat box so that I can answer. Welcome. So shall we conclude the session for this? If you have any more query, you are free to ask in any upcoming session. I have more session in this, so you can ask. So evening class will start at 5 p.m. please join the class. Okay, thanks, Dr. Niket Shastri. The evening class is going to start at 5 p.m. So whatever applications of MOSFET can be possible, those will be covered.